Hello everyone. In this video, I will show you what is actually happening inside a oscillator circuit. After watching this video, you will appreciate the Barkhausen criterion for the circuit point of view. So here we have a oscillator block in which we have an amplifier block and a beta network feedback block. Let us assume the gain of the amplifier is A and the gain of the feedback network is beta at a frequency omega naught. Note that this beta network is a frequency selective type, and it has a particular gain at omega naught, and the gain is less at other frequency. So gain is reducing at other frequency, and at omega naught it has a maximum gain of 0.5. So value of beta is 0.5 and value of A is 2 at a frequency omega naught. The spectrum of beta network I have drawn only for the positive frequency only, and it has the negative part also, which is exactly same as the positive part. So let us assume the circuit was off at t equals to 0. So a random white noise is present at the input of beta network. For simplicity, let us assume the amplitude of this white noise is 1. You can also take some arbitrary constant k, but for simplicity let us assume this is 1. Now at t equals to 0, switch on the circuit, and when the white noise passes through the beta network, it gets filtered out by the beta network. Because of this particular frequency selective nature of beta network, the maximum amplitude of the output spectrum is half and the minimum amplitude is 0.01, because here is the 0.01 and this is half, and this amplitude we have assumed this is as 1. So here it will be half and this will be 0.01. Now this modified spectrum will pass through the amplifier block, and it will come out from this amplifier block with a maximum amplitude of 1 and the minimum amplitude will be 0.02, because the gain of the amplifier is 2 and here it was 0.01. Now this spectrum, this will again come to the beta network, and because of this beta network the maximum amplitude reduces to half and the minimum amplitude will reduces to 0.002, that is over here. So it will be 0.002 and the maximum amplitude will be half again. So this is where the Barkhausen first criterion playing an important role. So now this spectrum will come to the at the input of this amplifier block, and its maximum amplitude will be 1 after passing through this block, and the minimum amplitude will be 0.004, because this was 0.002. Now this amplitude will come to this the input of this beta network. After that this amplitude will be at the output of this beta network, it will be 0.000004 and this amplitude will be 0.5, and again it will go to the input of this amplifier block. So at every circulation of the spectrum, the only frequency component that survive is omega naught, this omega naught. Here the amplitude will be 1, here the amplitude will be half. So this omega naught component only survive through this loop, and this is only for the condition that A beta is 1, that is the first condition of the Barkhausen, and this A beta equals to 1 at only at omega naught, right? And for other frequency, the A beta, the product of the gain of amplifier and the feedback network, is less than 1. So the amplitude of the other components reduces every cycles, right? So as you can see, after third cycle, when this spectrum is passes through this beta network, it gets reduces this amplitude, the components other than omega naught. So at the end you will have only the frequency component omega naught. Here it will have the amplitude 1, and here the amplitude will be 0.5, and the other components will be 0. And this circulation of this spectrum is so fast that you will get the pure sinusoidal signal from the output of the amplifier within a fraction of a second. So this is how we get the pure sinusoidal signal of frequency omega naught from from the loop. Now let us see why the phase condition is also important. Let us assume the phase condition is not satisfied by the frequency of interest. So angle theta, that means angle of A beta, is not equals to 360 degree or multiple of 2 pi. Let us assume that amplifier has a phase change of 180 degree and the beta network has a phase change of 170 degree. Uh, Let us also assume that at the input of this amplifier has a pure sine wave without any phase. So the output of the amplifier will be 180 degree phase shifted with respect to this input. And after that, this signal will pass through this beta network block, and it has a phase change of 170 degree. And at the output of this beta network, the overall phase change will be total 350 degree, not 360 degree. So 350 degree or minus 10 degree, that is equivalent. And important point is that this is happening at a frequency omega naught, right? So this minus 10 degree phase shifted output of beta network will go to the input of the amplifier block, right? But initially the input of the amplifier block has no phase. It was a pure sine wave. So because of this minus 10 degree or 350 degree phase change, there will be a loss of synchronization. So here is a loss of synchronization. So in order to avoid this issue, the overall phase shift must be 360 degree or 0 degree, or in general it should be a multiple of 2 pi. So this is what the Barkhausen's second criterion has to satisfy in order to have a pure sine wave at the output of the amplifier. Thank you. If this video is useful to you, then please like, share and subscribe my channel. Thank you.